It is a pleasure to have you spend an hour or so with us this afternoon learning about advanced nuclear and small modular reactors with Dr. David McNelis. He is a colleague of mine at the Institute for the Environment. He's a research professor emeritus. He has more than 50 years of environmental sciences and engineering experience in federal government, university, and industry settings. You can read more about the positions he's held on his bio that I sent you earlier. He's been a research professor in the Department of Environmental Sciences and Engineering at UNC, and he was also an adjunct professor in the Department of Nuclear Engineering at North Carolina State. But we know he likes Tar Heels better, right? Yeah, that's right. So he specializes in the environment and energy issues, really huge interest and bulk of expertise in nuclear energy, of course, but he teaches undergraduates about a range of energy topics and issues. So keep that in mind today as well as you ask him questions. And he's also, so he specializes in conventional, alternative, and nuclear energy systems and technologies and the nuclear fuel cycle. And so some of you have previously interacted with him in teacher workshops that I've done. I know we have some students in the webinar as well. Some are physics students and physical science students. So David has prepared some slides to walk you through. He has seen some of the questions that you've asked on Padlet, and then we'll also pause about 10 to 15 minutes before we end for Q&A. And you can also feel free to use the chat box, which you can find at the bottom of your screen, to ask questions. And I think everyone is muted, so we will kind of monitor you to make sure you stay muted. Anyway, I'm going to turn it over to you. Thanks for being here, David.
Thank you, and welcome. I'm going to be talking about nuclear reactors in general, how they work, but I'm also going to talk about small modular reactors and micro reactors, which is sort of a new endeavor. I have to find my little arrows again. If you walk into a thermoelectric power plant that's burning fossil fuels or nuclear, they're all the same. It looks something like this. You're heating up either with the fossil fuels or nuclear, and you're heating up a boiler. And the boiler generates steam, and it blows it onto a fan, or in the power plant, it's a turbine. And the turbine's on the same axle as a generator. And the generator is a magnet inside a cage. And as it spins, it generates electricity. So this is one of the two power plants that we generally have in the United States. It's a Westinghouse power plant. And one of the things I want to emphasize is that it's got a containment vessel on the reactor, a concrete containment vessel. All the reactors in the United States, and most of them in the world, except the one at Chernobyl, had a containment vessel. There's 3 loops in this. The first loop is the orange one that is going through the core, and it doesn't exit the containment facility. The second loop does, and it produces a steam that drives a turbine and the generator. In the United States, we get about 20% of our electricity from nuclear. In North Carolina, we have 5 reactors, and so we're generating about 35 or 36%. Isotopes, every of the 90 natural elements and all of the man-made elements, all of them have isotopes. And taking the simplest one, hydrogen, hydrogen has in the nucleus of the atom, it has 1 proton. And so anything with 1 proton is hydrogen. Anything with 92 protons is uranium, whether it's uranium-235 or uranium-239, all of them have 92. So the first one is hydrogen, which has only 1 proton. Deuterium has 1 neutron and 1 proton. And so you've doubled the mass. And so deuterium produces heavy water. And there's one reactor that uses heavy water. It's the CANDU out of Canada. And then tritium is the third isotope, and it has 2 neutrons and tritium is radioactive. The other two are not. When we mine uranium, it's 99.3% uranium-238 and 0.7% uranium-235. So 235 is really the one that we're interested in the reactors, all the light water reactors in the United States. And so in order to use it though, we have to enrich the uranium, the 235, to about 5%. So we do that, and then we have 5% 235 and 95% U-238. It's 238 in that bottom equation. So anyway, a neutron strikes the U-235, and so we've added a neutron, and it makes it uranium-236. U-236 is immediately unstable, and so it fissions into two fission products. We remember we had 92 protons, but now we've split them. So these are no longer, the fission products are no longer uranium. It could be cesium and strontium or any combination. And we also get, on the average, 2.5 additional neutrons, and we get 200 million electron volts of energy. I'm not going to mention the second equation here, other than to say that the 238 that's in the reactor fissions at about 1,000 times less than the 235. The little pellet in the fellow's hand is a ceramic coated uranium pellet. And so that is stacked end to end and then put into a fuel pin. This is the fuel pin here. And then they're put, they're put into the reactor, into the assembly. This assembly has about 290 fuel pins in it. And in a reactor, in one of our big reactors, you have anywhere from 150 to 300 of these in the reactor. And they're 15 inches to 17 inches on the side and maybe 15 feet long. So each fuel pellet, each of these little pellets that the fellow had in his hand, has the amount of energy of a ton of coal, 150 gallons of oil, or 2.5 tons of wood. And if you had 5 of these pellets, you know, you don't have a reactor in your home, but if you had 5 of these pellets, they would provide all the fuel you would need for a home for a year. The public has been concerned with nuclear. There's been 3 incidents around the world with commercial reactors. That is all. But people are afraid of a catastrophic accident, and rightly so. They're concerned about, and mainly governments, but people also are concerned with the proliferation of nuclear materials, nuclear intelligence, or nuclear people. They're concerned with a high-level radioactive waste. What are we going to do with it? We had a plan, and it was approved by Congress to move it to Yucca Mountain in Nevada. But Nevada is balking at that. They don't want it in their backyard, and they don't have any nuclear plants. So right now, the US policy is we'll store it on site in dry casks. And then the last item here is economics. A big nuclear power plant is very expensive. And once the plant's built, the O&M, the operations and maintenance, is about the same as a coal-fired power plant. So we had these 2 accidents at 3 Mile Island, and I say Chernobyl, but Chernobyl was not an accident. And then most recently, Fukushima Daiichi. At 3 Mile Island, the bottom line is there was a partial meltdown. About 2 million people in the area received about 1 millirem. And as it says, a chest X-ray is around 10 millirems. So the exposure to people was minimal. And so the bottom line on this is the partial meltdown resulted in significant property damage, but nobody died. This is Chernobyl, and this shows the RBMK reactor blowing up. This is the Soviet, during the Soviet days in 1986, and the Soviets built about 18 of these, and several of them are still running. As I was saying, I do not call it an accident. It was a consequence of poor design, poor management, and poor operations. All of those were very noticeable in what happened. They wanted to do an experiment which was extremely poorly designed, and the reactor itself was poorly designed. That particular reactor does not have a containment facility. They wanted to be able to, while it was running, pull some of the fuel out through the top and harvest the plutonium for weapons. It was known to be unstable at low power. They defeated some of the safety systems. They cut down on a lot of the water, and they removed some of the control rods. And the people were poorly trained, and there was just a bad safety culture. And then one of the main things, and the final thing that happened in the explosion, is when they put the control rods back in, they saw they were having a problem. They put the control rods back in. It was already partially damaged. The control rods didn't go all the way in, and it exposed the leading edge of them, which is 18 inches of graphite. Graphite is a neutron reflector. So as soon as that happened, the thing blew up. Now, when I say it blew up, it was not a nuclear accident. It was a boiler that the pressure built up and the heat built up and the pressure built up and the heat built up until it blew up. This is what a containment wall it looks like. And this shows it 4 feet, but they're 4 to 5 feet thick with heavy rebar all through them. On the inside, there's a 1/2 inch thick stainless steel liner. So they're almost an indestructible wall. Excuse me. This shows a map of Ukraine and Belarus and Russia. And you can see that the Chernobyl is right up at the north edge of Ukraine, above Kiev. And it's just about on the Belarus border. And then Russia is in green on the side. This shows the picture of where the Chernobyl is. And then the town of Pripyat was built for the people that were going to work on the plant. So it was built in conjunction with the building of the reactors. And they had 4 reactors at Chernobyl, and they were building 2 more. But anyway, number 4 is the one that blew up. And the separation between the village and the first reactor is 3 kilometers. And then this is a river that passes through, and the water for cooling was coming from this lake. You can see, this is the town. You can see it's a very vertical town. The reactor, you can see in the background at the top of the screen. This is, again, the vertical buildings, and this is their park. And then the bottom slides just show some of the damage that's been done to the place. I was at Chernobyl about 12 years ago, and I was allowed to get this close, right up against the fence, very close to the sarcophagus. The Soviets used 600 to 800,000 people to build this building over the reactor. So each person would go in for maybe a second or 2, and then get out and come back a month later and do it again. This is a monument to the construction. When I was there, the building was leaking and the water was running into it, and also the concrete was deteriorating. So they had to build a new structure, which has been completed now. And this was built in section on railroad tracks and slid in. But the point I want to make is you can see the size of it. It's 2.5 football fields across and 1.5 football fields in depth. So the Chernobyl was a major event in the world. It was the biggest nuclear issue that ever struck anywhere in the world. And so to study it, the Chernobyl Forum, with 8 different agencies of the United Nations, and all the scientists from Belarus, Russia, and the Ukraine studied it. And the results that they came up with the results they came up with of the 139 people that were on site at the reactor, 29 of them died from acute radiation syndrome. That's it's either an instant death or a very quick death. By 2005, 50 people had succumbed to the incident. The expectation from this Chernobyl forum is that up to 4,000 additional people, this would mainly be from the people that went in, the 600 to 800,000 people, so up to 4,000 of them could die prematurely, sometimes 50 years old when they would have died at 60 or whatever. But they'll be very difficult to track because people have moved around and they haven't been followed. There were also about 4,000 pediatric thyroid cancers. And the benefit, or the only good thing about pediatric thyroid cancer, it has a cure rate of about 99%. No excuse for any death, but that was the case. The personnel or the people that lived in that town were not really exposed. None of them suffered from acute radiation syndrome. So when I left Chernobyl, I wrote a report and I raised the question, is Chernobyl relevant with respect to the safety of current generation nuclear power plants? And that was a rhetorical question to me. If someone deliberately wanted to cause a partial meltdown, the containment vessel and the different water systems would prohibit it. In addition, most of the systems in a reactor and the people are redundant. The second question, is it relevant vis-a-vis the health risk, the dose effects, et cetera, and the international policies and procedures? Absolutely. There's a lot to be learned from the Chernobyl incident. This is Daiichi, Fukushima Daiichi. They had 6 reactors. These were GE, or at least the ones that had the damage were GE type reactors. And the thing I want to point out here is when a reactor goes down, if something happens, the electricity, when the earthquake happened, it kicked out their electricity. They had no electricity. The control rods dropped into place and they absorbed the neutrons, so it immediately shuts down. These reactors shut down within 1 or 2 seconds, and they go down to about 10 or 20%. The reason they don't go down to 0 is because the fission products are still producing a lot of heat and a lot of activity. But that would have been fine, and it could easily have been shut down by the operators. But what happened is a 42-foot wall of water came over the plant, knocked out all their backup water supply, et cetera. There was nothing to cool the cores, and there was nothing to cool the spent fuel that was in pools at the reactor site. So on to small modular reactors. What I was saying before, a lot of that applies to these, how the reactors work, et cetera. But the International Atomic Energy Agency identified small modular reactors as under 300 megawatts. And a big reactor is typically close to 1,000 megawatts or up as high as 1,700 megawatts. The benefit of these one of the huge benefits of these small modular reactors are they're designed to be built in a factory on an assembly line, taken by a truck or a nuclear barge or train to a site and then buried underground. So there's great safety and security. They're underground, and they're typically in sites like the NuScale, which I'll talk about in a moment. It's a seismic site. It cannot be damaged by a seismic event. It can't be damaged by an earthquake, a tornado, hurricane, or a plane crashing into it. The scalability refers to if I have a 250 megawatt plant in and then I need more power, I can add another 250 and add it to it. The siting flexibility, it's a very small footprint, and the full footprint, including the emergency buffer, is about 1/4 of an acre, very small. It's a manageable investment. It's a lot less than the big power plant, big nuclear power plant, and it's a lot less to run. It's very inexpensive to run because in a lot of cases you don't need somebody standing on top of it. It's below ground placement. It readily fits into brownfield sites. They're small and typically better than a 1/4 an acre. And they have an extended fueling cycle. All big reactors, we'd have to remove about 1/4 of the fuel every 18 months and replace it. So every 18 months, there's a downtime for replacing fuel on the big reactors. These want to have longer periods of time between any refueling or anything to do with it. So the scalability and factory prehab are very good. But the problem is if you want to do this, then you have to build a factory and ideally an assembly line. And you can't do that unless you have orders, a series of orders. So the other thing is that the process in the US is slow and tedious, although it's getting better. And they are doing things particularly good for the small modular reactors and the micro reactors. This is a cutaway or cross-section of the NuScale small modular reactor. And I show this one because it's one of the ones that will, it's already on order to go up to Idaho Falls. And and this one of the questions was at Idaho Falls, they're going to go with a full boat of 12 modules in the reactor. Each of these modules is 60 megawatts. So you can buy a 60 megawatt reactor and a control room. And they're placed underground. The control room also is underground. And then if you need another 60, you just add it and you do not change it goes into the same control room. And you could add up to 12. And all 12 are independently operated, controlled by the one operating. And so if you want to run 10 of them on electricity, and by the way, I should mention that Idaho plans to run 11 of them on producing power, and they're going to use one for research. You could have a couple of them. You could have one for desalination, and you could have one producing hydrogen, or all of them could do any one of those jobs, but all independently operated.
David, you have a question from Julia. Will they build a factory assembly line to manufacture the 12 SMRs for Idaho Falls?
I doubt it.
Okay.
I sincerely doubt it. That's not enough to do that. They also have, though, I believe they have an order for TVA and some orders from overseas. So that may be enough to warrant the beginning of a factory. This is a cutaway of one of the reactors itself. And the point here is the whole reactor, the steel-lined reactor, the core, is in water. So there is no need for pumps to pump large amounts of water or anything else in the NuScale reactor. And this shows a reactor this is a 45-foot reactor, 9-foot diameter, NuScale reactor going to a site. It's a cartoon of it, but that shows the size of it. And there's a fellow standing at the bottom here, so you can see the size of this thing. This is another one. This is a GE Hitachi, the Prism, again, underground. And all of this, the control rooms and everything else could be underground. The only thing that they would have above ground, perhaps, is the office or the administrative portion of the reactors. Now, this is a different kind. So far I've been talking about light water reactors. And in order to have a light water reactor, you slow down the neutron. The neutrons are coming off at about 14,000 kilometers per second. In a light water reactor, in order to have a good cross section with uranium-235, you want to slow it down to about 1/4 of a kilometer per second. So there are fast reactors with U-238 that do in fact use the fast neutron, and there are other ones that use the fast neutron. They're either fast or breeder reactors. This one happens to be a helium-cooled gas reactor, and it's using trisulfuel. So the fuel can be shown on the right-hand side here. The fuel can be constantly passing through here, and as it's used up, it's discarded out of the reactor. And this is what they look like. On the bottom right here, you have a kernel, which is carbon, oxide, and uranium. And that's inside multiple layers of silicon carbide layers that are protected from it. The reactors using these kind of fuels can go to very high temperatures. These cores, or these particles, the big particles, you can see on the top there, they're 92 millimeters, so it's less than a centimeter in size. They will not burn down or burn up in a reactor, and they can go to very high temperatures, which produce higher temperature steam, and which means more power. This is one I'm not going to get into a great deal with it, but it's one that Bill Gates has funded. It's a traveling wave, and this one uses plutonium. They can use spent nuclear fuel, uranium straight out of the ground. They can use depleted uranium in this kind of thing. And what you're doing is you're converting the uranium to plutonium, and the plutonium is the fuel that burns. And this particular thing is designed for 30 to 60 years without replacement of anything. Oh.
David, just pause here. We had one question about for you to reiterate the benefit from these being underground. Is it really but just because they're safer, they're smaller and safer, and you don't need all this refueling? And
the issues I talked about were safety. So underground is certainly safe, and I said they can't be affected by seismic tornadoes, earthquakes, etc. The other thing is, from a proliferation standpoint, it's buried underground. They're multi-year, so you don't have to do anything in terms of refueling, etc. And economically, they're much less expensive. So everything we talked about. Oh, and in these newer reactors do a better job of leaving less waste. So everything works out to the benefit of these things. And they're excuse me?
I just said, okay, thank you. I think that's good.
They're ideally ideal for isolated areas or remote areas, but you could use them in a factory, smaller ones in a factory or a plant, or even this overseas, certainly, because in the United States we can handle loads on large grids. Overseas, in some of the developing world, they don't even have 100 kilovolt grids, so they can't take anything big. Now here's two small reactors on barges. The bottom one is the academic Losemanov that was built and then sent up to Murmansk, where the subbase is, and then over to the town of Pevek. So it is now operational. It's got two 60 megawatt icebreaker reactors in it. And by Christmas of last year, it was in, and it actually lit up a Christmas tree, and I've got pictures of the Christmas tree, etc. The upper left-hand side is a Chinese concept boat, but they plan to do the same thing. For Russia, for example, this is ideal to get to the Arctic Ocean, and where they they have no power up there, no lines going anywhere, and they need a lot of power to develop the resources that are up there. The international community is worried about this because you've got a reactor on water, and if there is, for any reason, a meltdown or partial meltdown, it would cause a different type of issue, major issue. Now, this is microreactors.
David, I think someone just made, just check your make sure you're advancing, because we're still seeing the TerraPower slide.
Uh-oh. Oh, TerraPower, okay.
Yeah, we're on the Terra with the 3 circles.
Okay. Hold on one second.
So while we're waiting, I know some of you are entering questions in the chat box, and we'll be sure to get to those before the end. But if you do have questions, feel free to put them in the chat box. You could also add them to Padlet for David to look at later as well.
Did it move?
No, not on my screen. That's weird. Oh, there you go. Okay, so you just want to try it again?
Yes.
Okay. Okay, so now you're on the silicon carbide barrier coating slide. Yeah.
Yes.
Okay. Yeah.
Okay. Did it move?
Yes. Yes.
Okay, these are the 2 barges that I talked about. The lower right is the academic Losemanov that is in Pevek on the coast, and the other one is a Chinese concept one. This is the Oklo. This is really neat. It's a micro reactor, 1.5 megawatts. A big reactor again is 1,000 megawatts. This is 1.5. And it's designed for remote communities to operate for 20 years without refueling. So it'll power up a town for 20 years without refueling. Now, DOD just provided funding for 3 other companies to build small micro reactors, BWX, Westinghouse, and X Energy. And you can see that each of them received about over $10,000. Now, the idea is after 9 months, if they're doing well, each of these companies can get another $30 million to finish their product. And one of them will probably be selected to do a demonstration project. The other ones, of course, if they're not the demonstration project, they still have the reactor to build and sell internationally. Now, what DOD's objective was, in operations and certainly in battle, God forbid, that they use 10 million gallons of fuel per day, and which is humongous. And the additional thing is, particularly in combat, those transport trucks are ideal targets for the enemy. And so this would forego all of that. They want to generate anywhere from 1 to 10 megawatts of electricity for more than 3 years without refueling. So at the end of 3 years, you just replace the reactor or you refuel it. They want less than 7 days for a planned shutdown and safe transport. But when it goes on to site, they want it up and running within 72 hours. And this is kind of interesting too. They want it to fit in a 20-foot Connex container. This is a shipping container that you see at the ports. They want it semi-autonomous and not require man control to operators to ensure safe operation. Now I'm getting out to one other thing. In the middle of this, there's the electromagnetic spectrum that's defined by Maxwell's equation. And on the right, the frequency of the wave is more intense. The energy on the right is more intense, and the wavelength is bigger on the left. All three of these factors, energy, frequency, and wavelength, have a fixed relationship between them. So this goes from radio waves, where you have a very long wavelength, on up here to ultraviolet, X-rays, and gamma rays, which are very intense and a lot of energy. Now, the ones radio and microwave, et cetera, and light, what we receive from light, we're receiving photons of energy that actually energize us. And so all of this below in the non-ionizing, even though we're receiving energy from it, it doesn't really do anything. As you get closer to infrared in that, infrared does heat, and it produces heat. The light rays we experience, and then it gets on up into ultraviolet. At the upper end of ultraviolet, it becomes ionizing. That is, there's enough frequency and enough energy to actually disrupt bonds and to damage DNA. So stay out of the tanning booths. That's one of the primary message. But at any rate, then beyond that is X and gamma rays. And of course, X-rays are used, X-rays and gamma rays are both very similar. X-rays come from the electrons around an atom, and the gamma rays come from inside the nucleus. So we have three different types of radiation: alpha, beta, and gamma. Alpha radiation can't penetrate a piece of paper. It can't penetrate your skin. The problem with alpha is if you inhale it. Now, alpha is a particle. It's actually a helium nucleus, so it's 2 protons and 2 neutrons. So that's a very, very small thing, but it is a particle. And if you get it into your lungs, et cetera, it could cause bone cancer. Beta radiation won't, this cartoon here is bad. It does not go through your skin. If you got a large beta exposure, it would have look like a sunburn on a very small part of your arm or wherever part was exposed. It won't go through aluminum, and it won't go through your hand. Gamma rays do go through aluminum. They go through some lead, and they'll go through some concrete. And then neutrons, which are non-radioactive, go a long way. So alpha and beta are particles. Gamma rays are a phonon. Now, here's another thing to remember, and it's the middle little figure that looks like a little a. That's proportionality. So the intensity is proportional to 1 over d squared. So if you're near a radioactive source, if you move back 2 feet, it goes down by 1/4. If you go back 10 feet, it goes down by 1/100th. Go back 1,000 feet, it goes back down by 1/10,000th. So that's a very good thing to remember. And this is true of all radiation, not just radioactive. And so, questions or comments? Hey, we did pretty good on time. Is anybody there?
Yes, great on time. We have plenty of time for questions. A couple questions that came in while you were talking. Let me just go to my chat. And feel free to add your questions to the chat box. So let's see. Henrietta asked, and you answered this a little bit, but how many years is multi-year when thinking about these reactors? I know you mentioned a couple decades in some cases. But one thing I don't think you addressed was what happens, once those plants are spent, or if something does happen and there needs to be a cleanup.
You mean like Chernobyl?
For the small modular reactors.
It's very close. This is it's hard to say, but it is very close for anything to happen to them. Most of them are designed to be walk away safe.
Okay. So they would just leave the plant there once the fuel is
Yeah,
spent.
as a matter of fact, most of them, like the NuScale, if something happens there, it will shut itself down, will not require any additional water, and it'll just, because a lot of the heat is absorbed by first it's in water, and then secondly, a lot of the heat is absorbed by the soil on the outside. So it doesn't require anything.
And if there were some type of disaster, I guess the chances of that happening would be low, but I guess they have plans in place, right, in order to address that?
Yes, but it's, again, they're designed not to have that kind of thing happen.
Okay.
They're actually, you know, as I say, without anybody there, they'll shut themselves down. They won't require, this is NuScale, and they won't require any water, etc. Now,
go ahead.
A big plant out, you know, one of the big nuclear plants aren't, you know, these were built 40, 50 years ago. And so they don't have all of those in, although they're being designed and added to them as we go along. And any new reactors that are built will be that way. By the way, one thing I didn't mention on the Aurora, the Oklo reactor, the 1.5 megawatt for 20 years, that is a fast reactor. So it's going to be using the fast neutrons in its operation and run, as I said, for 20 years.
And where is that located? Do you know?
No, the first one is probably going to Idaho.
Oh, okay, the Oklo one.
Yeah, the Oklo, well,
okay.
Oklo and NuScale.
Okay.
The Idaho National Engineering Lab.
My question for you, and there's a couple other questions that aren't maybe necessarily related to the small modular reactors, but when thinking about all these advanced nuclear technologies that are smaller in scale, what is it? We do have high school students on the call as well as high school teachers. I'm just wondering what you would like for these audiences to know about these technologies in terms of, you know, do you really feel like we're going to start seeing these really showing up in our lives in the next 20, 30, 40 years?
The cost of big reactors is sort of prohibitive right now, partially because we're not using as much electricity. And the other thing is the renewable portfolio standards that are in the States require 12% to be from wind and solar, and nuclear is not mentioned in there. So nuclear is taking sort of a hit from that. And so it's just not economically feasible to build them. Now, having said that, there are two large reactors, two Westinghouse reactors that are under construction in Georgia. I think one of them is about ready to go, and the other one is not. The small reactors we are going to see. I would expect within 2 years we will have small modular reactors up and running. By the way, we have a lot of small modular reactors operating in the Navy. The submarines, all our submarines are nuclear. All our warships are nuclear, and they're, you know, they're maybe about 80 megawatts type reactors.
Okay. So some other questions that came in. Cindy asked, where are we in the production of the fusion reactor in France? Is this potential in our future? So if you could speak to fusion quickly, or
well, any rate, if you take a U and you draw a big U on your plate with a little bit spread out on the top, on the left-hand side is the lightest elements, and on the right-hand side is the heaviest, the big molecules. And so on the left is for fusion, and so hydrogen is the very left item on there, and that's excess energy per nucleon. And on the right is excess energy per nucleon, and that's the things that will fission. So on the left, it's fusion. On the right, it's fission. And, you know, typically with fusion, we're looking at the isotopes of hydrogen. We're looking at deuterium and tritium. And so you'll have DT reactions or DD reactions, et cetera, and they produce a lot of energy. Now, what's happening is there's many different fusion experiments going on in Princeton, at Stanford, UCLA, Berkeley, et cetera, and at the ITER in France. The United States is involved in that, is China and Russia and the EU, et cetera. That, one of the issues with that, they have this big metal box and a tube, a metal long pathway for it. And they're trying to hold something in there that's 15 times hotter than the sun. So right away, you know, say, well, you know, how are they going to do that? Well, then they have to do special either electric or magnetic fields, or to isolate the plasma in the center of that tube. So the ITER, they claim it's been 25 years off for the past 25 years. But I really think now, I really believe that we're getting less than 25 years off for that. And the other thing is, other people are trying other projects. We are able to do fusion. I had a doctoral student at Berkeley that actually used a small modular fusion device. But the difference is that's a batch process. It's not continuous. And in order to be commercially available, it has to be a continuous process where, you know, it's running power plant, or it's a power plant that's providing power for the city. And there's no waste that comes out of it. So it's a clean process. But I truly think we're getting closer. But we're doing the fission reactors, and particularly, I like the small modular reactors. These small modular, like the ones that the DOD is funding, and the OKLA, the fast reactor, those are really neat, and they're 1.5 megawatt. If they fit in a Connex container, they could be in a parking, or not in a parking lot, behind a factory or anywhere else and operating. So, and they're great for distributed, if small towns are just things. The other thing is, we have 120,000 miles of grid in the United States to produce, or to pass electricity. And it's run by 500 different companies. So these companies, well, the grid itself, the companies probably like to play well together, but the grid doesn't always play well together. So the only thing that we've ever done that was really, really good is under Eisenhower, we created the interstate highways. And that's like starting with a clean sheet of paper and building something over the whole country. That's what we should do with the grid, but that's trillions of dollars of cost. So we're trying to figure out ways of doing it to match up the grids. So this distributed system is one way of taking some of the elements that will feed into the grid off the grid.
Mm-hmm. Yeah, and it seems like it would help for the entities using the small modular reactors, give them some greater energy resilience.
Yes.
Another question came in from Robert about thorium reactors. So just what about thorium reactors that use molten salt? Could you speak to that?
A bit. Molten salt is well, excuse me, thorium is a very good fuel for reactors. It's thorium that you convert into uranium and then burn, but it's a very clean fuel. It doesn't produce near the waste that uranium does, etc. There's experiments going on in the United States to develop it. India actually uses thorium on some of their reactors, and they're probably well, they're a lot more advanced as far as thorium is concerned than the United States. We elected to go with uranium. One thing people are concerned about uranium and whether there's enough of it, et cetera. But I mentioned with the fast reactors, you don't have to enrich it and you can use it right out of the ground, or you can use depleted uranium. And then the biggest source of uranium, if we ever came to need it, is in the oceans. And there's a lot of uranium in the oceans. Did that help?
I think so. And that's all the questions in the chat box. So I was going to ask you all that are still on, feel free to unmute yourself and ask a question. In particular, any students on the call, if you want to ask a question, and it can be about nuclear, it can be about careers and energy. It could be, we have time. So
there was a question about what % volume of the containment space is vacuum. And that's,
right. Okay.
The answer to that is none.
Okay.
Will small modular reactors bring us into a new way of obtaining energy? The answer to that is yes.
Yeah, it sounds like it.
SMRs safe for the environment? Hugely. How big is an SMR? And I think I explained that thing that looks like a cabin that you might have on a river somewhere for the Okla, and then the 20-foot Connex container. So those are very small reactors. And then the as I said, all of them are, the small modular reactors are all underground. I mentioned the emergency protection zone for a big reactor like the Harris plant or the ones we have in North Carolina. It's like a 10-mile zone that you want to very closely monitor that 10-mile zone. When we're talking about small modular reactors, you're talking about something like a quarter-acre footprint, and that footprint is just about the size of the emergency protection zone. So there's a huge difference.
Mm-hmm. So let me just pause for a moment and see if anyone wants to unmute themselves and ask a question.
Hi, I have a question about the zone, the 10-mile zone. You said that it's closely monitored around Sharon Harris or some of these other power plants.
Yes.
When you say monitored, how and what are they monitoring for?
Well, the one thing they're obviously looking at is any radiation, the fence line radiation at that distance, and it should be zip. So well, I guess that's the main thing. The other thing that they have for that 10 miles is if there was an accident, if there was a partial meltdown, then they will distribute, and they probably have already distributed, the potassium iodide pills. Mm-hmm. And the issue and why they issue that is iodine, which is one of the fission products. Iodine goes to the thyroid. And so if you use the potassium iodide, you block your thyroid so no more can go in there. And for babies have about a 9-gram thyroid, and so it doesn't take much iodine, radioactive iodine, to give them a problem. So again, you block that. Does that help? Hopefully.
Yeah, she might have muted herself. That was Cindy. And there's also, I've noticed from driving around the Harris plant, that there are sirens up as well. So that area can be quickly notified, if there were an accident. They have the system in place. And we're getting short on time. I thought maybe I'd ask you to speak just a little bit about careers in nuclear, and kind of where, again, some of the students on the call might be interested in energy, nuclear energy. So maybe just speaking to that. I know the workforce is retiring and they're training students at State, for instance, to be nuclear engineers.
Yes, so for a while back, there was a nuclear renaissance. And before that, the number of students over at NC State in the nuclear area was rather small. And one year I had 2 doctoral students that graduated. And those were the only 2 doctoral students that graduated from that program. But now, then the Renaissance came up, and the openings for nuclear were immense. And so a lot of people went into it. And I think the number of students over there are large now. And I think the advent of the small modular reactors will largely add to that.
Mm-hmm. Yeah, I was wondering if any teachers on the call had already introduced small modular reactors to their students. And if so, what you've done. Does anyone want to speak up to that? Has anyone already done this? Wants to share? And I'll say too, like a lot of the reactors that David mentioned, you know, a lot of like NuScale, you know, going to the websites for these companies is a great place for your students to go to see pictures, learn about the technology. I think having your students figure out why underground is better for so many reasons, and why these smaller technologies, all the benefits. So hopefully you're seeing some good connections to the curriculum that you already have to teach about in terms of energy, or if it's physics and chemistry, et cetera. One question from Julia, she says, North Carolina State is graduating 20 seniors as nuclear engineers a year. What do high school students who want to attend a community college for 2 years do? Is there a nuclear tech program?
Probably not. But if they take, you know, one of the things that NC State is big on is modeling, mathematics. So those kind of things, computer science, all those things would be immensely helpful in entering it maybe after 2 years into the NC State program.
And what about like electrical engineering, doing something like that at the community college level? And then
that would be hugely helpful.
Okay.
I went through probably 30 students, master's and PhD students at NC State while I was over there.
Yeah, there's quite a number. Many of the teachers on the call have been with me to go tour the reactor at State, where we met some of those students, and it was also great to see a number of females involved in the program as well. We are just about out of time. So David, I want to thank you so much for spending an hour with us, and I think everyone found it useful.
Dana,
and yeah, go ahead.
For you and for the teachers, if there's anything else or other groups that you would like, I would be glad to do this type of thing.
Great. Yeah. And if you have follow-up questions, feel free to email me and I can connect you with David. You can find his email also on the website. I am particularly interested in hearing from any teachers who have introduced this technology to their students, because I'd love to know what you do and what your students respond to. And I can forward that to David as well. But I think at this time it's right at 2 o'clock. So I want to wrap up and just thank everyone for being here. And, you know, if you have any final questions, we can hang around for another minute or two. But I know a lot of people are starting to head off. So thanks everybody. And thank you, David.
You bet.
It sounds like Robert Tufts has shown a TED Talk by Taylor Wilson. I don't know if you've seen that. SMRs. I'm just talking aloud to whoever's still there.
Okay.
I'll have to look for that. Great. We've got a lot of thanks for coming in on the chat box, so you can see that if you'd like.
More questions?
Just a lot of thank yous. And then Angel is asking about what can we expect in terms of using nuclear power in aircraft, if you want to answer that.
Spacecraft, not aircraft.
And why is that?
I think because the two things. One is the potential exposure to the people on the aircraft, the weight of the reactor, and what happens if the airplane crashes.
Right. Okay.
Now, you know, we have nuclear weapons on aircraft, but those are not armed.
Mm-hmm. Okay, hopefully that answered Angel's question.
But as you see, they are on submarines and warships, and you saw the two barges,
Uh-huh.
the academic and the Chinese one.
Okay. All right. Well, I think that's it. Robert did put the link in the chat box for that TED Talk he mentioned about small modular reactors. So we'll all have to watch that, see what that's all about. And yeah, I hope some of you are inspired today to introduce your students to the topics and have them figure out the answers to some of the questions that y'all have asked. So thanks, everybody.
I'm signing off.
Yeah,
Thank you.
thanks, David.
You